Okay, welcome back to the undergraduate seminar, everyone. I am super duper excited to have Albertly here, who will tell us about partial orders and applications to the semantics of computer programs. Very excited to have a math, computer science talk today. Thank you for coming out and speaking, Albert. Take it away.
Okay, thank you. And so that would be the question we are going to answer today. I have some program, and for simplicity, let's say just a functional language, and I know the type of a recursive function and the domain and the codomain, and I know, well, it is very boring. It doesn't really do anything, but it is designed to not terminate for some inputs and terminates and gives you some boring answer for some other inputs. So this is what we expect. We expect this function to be defined, well, g of n, if you actually have give a number n as an input, well, you have an answer for some, for some input, and we expect it's undefined for some other input, and this should be fine, this should be allowed. And we want a mathematical model that gives, that agrees with this and gives that prediction. So one thing, the first thing we do is we say, okay, the codomain is integer. Actually, we're going to say the codomain is going to be a little bit more interesting than integers. It also, the codomain allows saying that things could be undefined. So we do that. And in general, we will also do that to the domain, because it is more uniform, because you want to say, because it would, well, if what I do today, you could ask, why do we just add a special value? We're going to call that bottom. And it is written like this symbol that tries to be a tag that is sitting at the bottom. And it stands for no answer. So we can, so you go back and say, hey, so this integer, right. So this, the codomain integer, well, we do that to the codomain. Why don't we also do that to the domain? Yes, in general, we should. And it would also cover a lot of interesting language features, but it is going to be distracting if I do it to both the codomain and the domain. So for my very simple example, I will just do this, right? And there is some fine point is, because you say, hey, so we use a special value to stand for non-termination. Well, that's the intuition, because if you, we think of computers, we think of actually the computer will be performing a lot of steps. And if it turns out to be infinitely many steps, then yeah, that's non-termination. If it turns out to be only 1 million steps, then it terminates. But the model here tries also to abstract away from the computational steps. We don't want to even commit to any notion of steps, taking steps at all. We just talk about, I have an answer, I have no answer. So with that, there's no such thing as non-termination, because, and there's no such thing as termination either, because there are no steps to talk about. So, so eventually you will have to accept that we are just talking about, I have no answer, I have undefined, or I do have an answer, I have some information, I have no information. The second thing, now that we are allowed to declare that a function given an input, then it maps a certain number. That function can map a number, a perfectly valid number, to the undefined symbol to bottom. If you allow that, then we are going to construct a sequence of functions G0, G1, G2, and they will be approximations of the ideal piece of code. And the first element, the first function in the sequence is very boring. It maps every input to bottom. Now, the other the other guys, the other functions in the sequence are going to build upon one another, right? So I will be defining g of I plus 1 in terms of g of I. And I say, okay, and basically I copy my code, or rather I use, well, see here what happens is most of the code, we already have a very good mathematical model of them. Yeah, this equal, well, we know what equal means. If then else, we also know how to model if then else in mathematics. So most of it, we all pretty much know how to model them in mathematics. It's the recursion that needs work. So we say, okay, at the site where we make a recursive call, we don't call the function we are defining. We call a function that is already pretty much we have nailed down before, right? If you have defined what G0 is, then we know how to define G1. G1 will be saying, if you make a recursive call, we'll just call G0 instead of calling G1 itself. G2 will be calling G1 when this is recursive call. So we have broken the cycle. We do not do recursion now. We just say we call a slightly different function, my predecessor. So you work it out, and so yeah, so G0 maps every number to bottom. G1 is a little bit better. G1 0 will give you 0, but otherwise it will behave like G0. So otherwise it's bottom. G2 is a little bit yet better than G1. So G2 says if n equals 0, then the answer is 0. So the base case gives you this 0 for G2. Otherwise, I will call G1 n minus 2. So for example, G2, if n equals 2, we say, okay, n is not 2, but n equals 2, so n is not 0. So we'll call G1 of 2 minus 2. So that would be G1 0. Oh, okay, G1 0 is 0. So there we go. And so you can do this, and you can go home and do this a little bit more, and you find that G3, G4, so G10 is going to be an improvement on G9 by a little bit. And so these all approximates the program, and it was the ideal recursive function. In what sense? In the sense that G3, for example, is as much information as you can figure out if you allow yourself only a quota of a known recursion depth and well, recursion depth of 3. So G0 knows nothing because because it's not allowed any quota at all. G1 allows something like maybe recursion depth of I or I plus 1 I might be off by 1, right? So and so bottom stands for no information. Sometimes it also stands for I don't know, and I don't only because I don't know for now. But in the ideal case I would know. But if given this very limited recursion depth, I don't know. I don't have an answer for now. I'm not, and I am still not committing. Maybe there's an answer in the future, but not now, not up to this point. Okay. So now, well, so you see this is a very good trend, and this trend seems to be covering more and more of your domain. And so you imagine, and this would be a general formula if you want to write down a short formula that covers the general case for the approximations. And but intuitively, it is a sequence of increasing improvements and definers. So you would expect there's a way to define a notion of limit so that you can say, hey, take limit of this sequence, and that will be exactly this, and that will be exactly what you want to predict, and that will be your mathematical model, and which gives the prediction that we expect that we expect to make sense. G of n should be 0 whenever the input n is a non-negative integer and is an even number. And otherwise, G of n will be undefined. And we'll have to define what limit means. So and this is a general recipe. You have a function, you have a piece of recursive code that calls itself with a slightly different parameter. If you know the domain and codomain, then the model, the mathematical model of this function will be, well, you find a mathematical model for your data type, but the codomain needs to allow undefinedness. Maybe the domain also needs the same notion of a similar notion of undefinedness. But today I will do the simpler one, but in general, you will want to do the more uniform one. And that can also answer more questions. And you say the model of foo, the function foo, well, will be, well, how to obtain a model of the function foo. So you define a sequence of functions, and you always start with the first element, the first function always start with saying, I am undefined everywhere. And then the other functions in the sequence will be improvement upon the predecessor. And when you need to make a recursive call, you say, I don't call the same function, I call the previous function. And so everything is on very good mathematical ground, at least for this sequence. And then now we just have to worry about what do we mean by limits and why does this recipe always work? And but if you know what this is what I sometimes do to understand some recursive functions, then this is already this is already a very good well, at least very good knowledge. This is sometimes I actually do this for some tough recursive definitions that I don't understand. So I work out a sequence like this, and then I see the trend, and oh yeah, so and now I understand more. I'm more comfortable with that. Sometimes I don't. Sometimes I do. It depends on what kind of difficulty I run into. But of course, the mathematical question, the math question is, of course, why is this always a good thing to do? Why is it legal? Okay, so to explain that, but we will be talking about a lot of math about partial orders and some extensions, some extra conditions. Partial order, well, you know total order, like you can compare and say, compare two elements and say one element is bigger than the other or they're equal. And it's always x less than y, or x bigger than y, or x equals y, and x and y are always comparable. That would be total order. Partial order says, okay, sometimes some pairs might be incomparable. Sometimes it might be true that x is not less than or equal to y, right? And not the case that y is less than or equal to x. And this funny symbol will be, we would like to use, well, I will be using this symbol for most partial orders. Sometimes I mean this symbol to be a general arbitrary partial order, and I want to use it to state a general theorem. Sometimes this stands for a very specific partial order that I will need for explaining recursive programs and why recursive programs exist, right? But and of course, if you like, I will also state the axioms very carefully. Your relation is reflexive. It is a reflexive relation. It's also a transitive relation, like that. So that you can do inequality chaining, basically. And then anti-symmetric. So if x is less than or equal to y, and also y is less than or equal to x, then you do have, then you can conclude that y is equal to x. And we are just missing a requirement that if you have an arbitrary pair of elements x and y, one of these two must be true. Total order would be insisting on that. And a familiar example, well, of course, there's also every total order is automatically a partial order, but that's boring. So for an interesting non-total partial order, you have seen all of us have, most of us have seen sets and the subset relation. So if you have a power set and you say, I want to use the subset relation as the relation for the sets, for my sets inside this power set, or really any family of sets, then that would be a partial order, because it satisfies all these requirements. Okay, so the specific one specific order I will need today is what people call the information order for those sets where you have a lot of values, but you also add a bottom to say sometimes a certain function gives you no answer, so it is undefined. So this information order is defined, well, at least for this case, is, well, there are two things we want, well, two kinds of things we want to be true. Bottom should be less than or equal to k, and of course bottom is, well, we understand that bottom is not equal to any of the integers. The bottom is less than or equal to, oh, I screwed up. It is not just that, it's also, I also want to do a little bit of a reflexive transitive closure, because I want bottom to be less than or equal to itself. So maybe I should, oh, it is a very easy fix. Bottom should be less than or equal to itself, but bottom should also be less than or equal to all of the actual integers, and of course not equal to the integers. And also for every integer, it is less than or equal to itself. But what is missing is different integers, they are incomparable. And the name is information order because the motivation is this: when x is less than or equal to y, where x can be bottom or an integer, y can be bottom or an integer. But in all cases, when this is true, it should mean, we want this to mean that y has the same or more information. Y has the same amount of information, in fact, the same information as x, or if not, then y should have more information than x. So for example, 42 is declaring that it is 42 is the answer. Having an answer is of course better than having no answer. So 42 should be above bottom. But 42 should not be above 0, because 0 is one valid answer from a certain piece of code, and 42 would be a valid answer from a different piece of code, and they should, and none of them is more informative than the other. We have basically hit full information in both cases, so they don't win over each other. But bottom loses to an integer, because an integer says you now know the answer. So y above x, when x is below y, we wanted to say that y knows more about x, or y knows the same thing as x, right? And people will be writing this shorter symbol z with a subscript bottom. Hazy diagram is how you can draw these very abstract relations in a very nice picture. And in general, if you have two elements x and y, and x, and you know that x is less than or equal to y, you know what? I like to just say x is below y, and expect you to understand that I also mean x could be equal to y. I don't, right? Less than or equal to is a very long thing to say. Well, I could also say y is at most x, but yeah, that also works. But it is, but then the English phrasing is in the reverse order of the notation I write out on the blackboard. So sometimes I want to say x is below y. It just means, and when I say that, I already include the possibility of equality. But in case they are not equal, and in case there's nothing in between x and y, then you find some place to draw y and some place to draw x, but make sure that x is y is draw a little bit higher than vertically higher than x, and you connect with an align segment. And horizontal position is up to you, just as long as you don't make a mess. So this would be an example of a power set and using the subset relation on the power set to be the partial order. That would be a portion of the information order for the integers together with undefinedness. And this would be an arbitrary set with an arbitrary with some contrived partial order to become a counterexample to some of the definitions later on. But of course, eventually this serves as a very interesting counterexample to certain things that we don't like, but just to show you that sometimes some naughty partial orders are possible. And I have A, B, C, D being 4 different elements. But you could have this, and you can check. You can check that this is a partial order. It doesn't break any of the axioms. Okay, so this information order over the integers with one extra symbol or one extra distinguished element for bottom. Yeah, this is a very boring order. This is a very boring order, but from it, we can build up more interesting orders. So one of them I need today, because I also talk about functions, and I'm using functions, but just funny functions to model recursive programs. Yeah, functions with funny domains and codomains to model. Well, so I will be talking about functions as well. So from this, you can build up a more interesting order on your function spaces. So here's one. So the function space will be from X to D. I have a partial order over D. So for the codomain, I know, and I have a partial order, and usually it will be, it is the information order. The domain X, today I don't need any structure or required structure on X. So that would be the function space. And some of you may like to write it as D to the X. I like to write as X arrow D. Keep writing that, but if you don't like that, then imagine I'm writing the exponentiation. I'm writing the exponentiation set, or even the exponentiation object. Yay. So we are going to take the order, partial order for the codomain and extend pointwise to the whole function space. And in this function space, suppose you have two functions f and g in this function space, and we declare that f is below g if and only if for every input x, you take a look at f of x, you take a look at g of x, and you find that f of x inside D is below g of x inside D. So on this side, once you have candidate inputs to consider, then you can use the partial order given for D, but you use this to help you define a partial order on this function space, and so that would be the reason why when I write down G0, write down a snapshot of G0, G1, and G2, and so on, write down some samples, I write it G0 way below, because G0 is now less than, in fact, strictly less than G1, because we're comparing pointwise, and yes, so let's see, every point, for every input, G0 n, for every n, G0 n is the same as G1n or below, strictly below G1n. So you can compare that, and so G1 is less than G2 and so on. So, so G0 is really below G1 and so on. So that would be an example of doing that. That would be the interesting order that I need today. And this is why the information order on the codomain needs to be very boring. We need that much safety because we want G1, suppose we know G1 well, we know G1 is below G2. We want this to mean that G2, not only is G2 more defined, not only G2 works for more input than G1, but also wherever for those inputs that works for G1, G2 has to work the same way, right? So that is why the order for the codomain has to be very boring, so that the order for the function space actually is very meaningful and actually gives you a very good sense of very consistent improvement. When you do improvement, you don't change what is already known. You only change from some previous unknowns to new knowns, but previous knowns, you don't want to change that. So that's why. So that's a very useful order, even though it looks very boring, but very uninteresting. This is a very interesting order. This is somewhat interesting as well. This is uninteresting, but that's because we need to use it to actually build up some useful and safe function order on function spaces. Okay. So join or list upper bound. So sometimes list upper bounds exist, sometimes they don't. But at least we can define what we want out of the list upper bound, and then we can talk about under what scenario they exist and under what scenario they don't exist. So first, the version where you only have two operands. You have two elements from your set B, and we have a partial order, and depending on the partial order, depending on D, depending on this partial order, and depending on the individual elements X and Y, the following may exist or not. And a list upper bound of these two elements may or may not exist, but when it exists, we write it as in this infix operator notation. And to spell out the axioms or requirements very carefully, this join needs to be an upper bound, so X should be less than or equal to the join of X and Y. In general, well, basically we say each operand is less than or equal to the join. The join is an upper bound of each of the individual operands, and it needs to be the least of all upper bounds. So if you have some set prime, arbitrary set prime that comes out of the blue and turns out to be an upper bound for both X and Y, a common upper bound, then our join should be less than or equal to this other out of the blue upper bound, and maybe equal as well, because this set prime could also be X prime Y itself. Right, and an exercise for you when this join exists, it is unique, and basically you try to use the least, this requirement about being the least, to show that if you have two least bounds and they are less than or equal to each other, so they are equal. Oh, that spoils the exercise. I will not do it again. Well, we have a lot of other exercises for you. So it is just a very simple maximum if you have a total order, but that's boring. So union would be, so if you use a power set or a family of sets and you use subset, the subset relation as or containment relation as the partial order, then union would be the join. And from that experience, you realize that for a total order, the join has to be equal to one of the operands. But then when you have a non-total order, and you know this from your experience with playing with set unions, the answer of the join can be very different from both operands, can be more than both operands, right? So right. And here is so sometimes join does not exist. For example, right. For example, in our information order for the integer and bottom, if you take 0 and 2 or take 1 and 2, there's no upper bound at all. Okay, so that would be one way when a join does not exist. Another way the join doesn't exist is this kind of naughty partial order that is not very useful for my purpose today, but still, it is a good counterexample. It's a good example to keep in mind to find out that it makes a lot of things break, a lot of definitions break. So A and B has two upper bounds. C is an upper bound of A and B. D is an upper bound of A and B, but C and D are incomparable. So none of them qualifies as the least upper bound. So this is an example where a least upper bound, a join, does not exist. And it is because you have too many candidates, but they are incomparable. They're all, you don't know how to break the tie. And this example with the information order is where sometimes you don't even have any upper bound, any common upper bound, so you don't have, so you may, sometimes some joins don't exist. Okay, but of course, if you say, oh, the join of bottom and 2, well, that one is 2, but the join of 1 and 2, that doesn't exist. Yeah, so that and that you have a lot of incomparable upper bounds, so no one wins. Well, that's too easy. The join of 2 elements, and you can use induction to extend to the join of finitely many elements. And you have, if you have bottom, then you also have the join of no elements at all. But how about an arbitrary set? And in this case, of course, the interesting case is when you have an infinite set. So do infinitary joins exist? So we define, so yeah, so the join of a lot of, you have a set of elements, subset of D, a join of that set, or rather, or maybe the join of the elements of those of that set may or may not exist in D, but when they exist, we write in this symbol a big, just like you try to write some big summation symbol for or a big, big something symbol. So we write that, or if you prefer to write out in the index form, then you write out the join of a lot of some expression that uses a dummy variable I, and that I ranges over a certain index set. So you are doing a join of a lot of guys, a lot of elements, and you use an indexing scheme. And exercise for you when they exist is unique. And the I don't have the axioms, but it's least upper bound, right? So it is like, so it is a generalization of being upper bound and being least. So maybe I just say in words. I think it's because I do have space for those. Yeah, I could add them back. Every element in S should be below the join, right? So that the join is an upper bound of every element. And it should be the least upper bound. If there's some element out of the blue that turns out to be an upper bound of all elements of S, then the join should be below that out of the blue arbitrary upper bound. I think I decided to not write it out because if you have known about supremums, when you learned about the real numbers and do a little bit of introductory real analysis, but it's exactly the same, writing down the same axioms as supremum. So example, if you do arbitrary, you can do in the power set, even if you try to do a union over an infinite number of sets in the power set, your power set is very big. You have you have infinitely many sets, and even if you try to do union of infinitely many sets, it still makes sense very nicely. So these are examples where I have total orders, but you have some experience from real analysis. This set does not have a supremum because because you are limiting yourself to the rational numbers, and this. But if you relax yourself to the real numbers, then and you do have a join. And we will be able to define a notion of join for functions in those function space, in the function space where the codomain is a partial order that also has that in a partial order, and but suffice to say, it will turn out that that sequence of function gi, a join exists for that sequence. So this is when I want to use the indexed notation, and so this join business, the least upper bound will be our notion for limit, and you can kind of you also can kind of imagine that this is some kind of union of all those g of i's, because that undefinedness, even though it is an element of our set, it is of some kind of second class citizen, and we don't really like that. So if you have a lot of gi's, you can think of merging all those gi's as some type of union where the bottoms goes away when you have an answer. Okay, so now these joins, whether it is the join, even the binary case when you only have two operands to worry about, sometimes it doesn't exist. And by the time you talk about an arbitrary, possibly infinite set, it has an even higher chance to exist. It's a tall order to insist that a certain element of set, so that a certain set of elements, a certain subset has a join. So now we say we focus on those partial orders or those sets with partial orders with an extra property. So we don't require every arbitrary set, a subset, to have a join, but we want to require certain special subsets to have joins. So these are called complete partial orders, and it will turn out that the requirements of complete partial orders are nicely satisfied by the partial orders we use to model codomains and domains of computer functions. And also the function space, eventually if you put some restrictions on the function space, it will turn out that they satisfy these very nice requirements. And on the other hand, these requirements allow us to prove that recursion exists. The recursion exists if we are working over this CPO. So the complete partial order, and I will be saying CPO because this is such a long name, and CPO is used so much in this area. And so, well, maybe the easy one first. Your partial order, your set has a least element, and exercise for you prove that it is unique. So and it is the join of the empty set, because basically it's the identity of the binary join operation whenever it exists, and that usually we will again call that bottom and use the symbol. So your set B has a least element under this partial order. But the interesting one is every chain has joined. So what do I mean? So suppose you have a subset S of your D, and this subset suppose is non-empty, but the empty case is kind of taken care of by the second cross. This second cross is usually written in separately, because some people want to sometimes say, I only require want to think about non-empty subsets. I don't want to worry about a least element. But sometimes you do, sometimes you don't. So some people like to, and some people don't like to. So we sometimes write these two separate, even though I know how to merge them into one single thing. But suppose you have a non-empty set, a subset S of D, and if you restrict your partial order to this S subset S, then this partial order becomes a total order. So in other words, if you pick an arbitrary, if you pick a pair of elements X and Y from S, then X and Y are comparable. So every pair of elements from this subset S happens to be comparable. And in that case, we call, there's a name for that. We say that S is a chain. So when S is a chain, so this partial order set, so CPO says maybe very arbitrary joins don't exist. If you have a very arbitrary set, maybe it doesn't have a join inside this set using this partial order. But if your set is a chain, if your subset is a chain, then it has a join, that join exists, and that join is an element of D. So now example, an example is the power set. If your family of sets is very nice, it's the power set or a power set, then then actually arbitrary union exists, and so union of a lot of sets that are comparable with each other, of course, that also has a union. Now, the interesting example where sometimes union doesn't make sense, but some other time it does, is the set of all subgroups. So we pick a group, pick an interesting group, a group you like, and don't make it too trivial. Well, actually, it was also work for the trivial group, but very boring. So pick a group you like, even pick a very large group. So now you look at all the subgroups of that group, and that forms a set. Now, if you pick up only a few subgroups, or maybe an infinite family of subgroups, but make sure that every two subgroups in your family are comparable. Either, one of them is a subset or equal to the other, then just forming a simple union of your family of subgroups, that will make sense, and that will give you a subgroup again. So that would be interesting. And so that's something nice. That's something you don't usually expect out of arbitrary subspaces, subvector spaces, or subgroups or submodules. But if you have a chain, then union will work. Union will give you back a subgroup or subvector space or submodule, something like that. The information over this, so this is a very boring order, but this is this one is because it's really boring. There are only very limited kinds of chains, and they all work very nicely, right? So let's take a look at that picture again. Right, so a chain, maybe your chain consists of zero and bottom, right? A chain requires every pair of elements to be comparable. So maybe your chain consists of zero and bottom. Okay, well, that certainly has a join. Maybe your chain only has zero, but that will have a join. The answer is zero. Maybe your chain only has bottom, so so the join is bottom. Your chain cannot contain both 0 and 1 because we require a chain to every element, every pair in the chain. We require that to be comparable. Well, if your chain has both 0 and 1, well, that is not a chain. So a chain is very limited for this order, for this partial order. So every chain has a join because it's really a boring case. This, and this, and this. Okay, but if you extend that order pointwise to this function space, then you also get a CPO. That's the interesting part, and the proof is on the next slide. In general, if your function space, your codomain of your function space is a CPO, then the pointwise order for your function space will be a CPO as well. And I am going to run out of time very soon, so I will skip the proof. But one of them is, maybe I'll just tell you the gist. So the smallest possible function in this function space is, of course, the very trivial function that says I map every input to the least element. But this D is a CPO, so it has some kind of bottom. So if you map every input from X to that bottom, you have really hit the rock bottom of all possible functions. So that one is taken care of. And For the join, you do the join pointwise. So if you have a set of functions and you know that it is a chain of functions, then you say, how do I compute the join of all those functions? Well, so you say for every input, give that input to all of the functions in your set. So you have a lot of elements in D now. So, and this turn out, it will turn out that this set, you can check that that set is a chain in D. So it has a join. So use that join for the answer for your combined, for your candidate function for that input. If you do this for all inputs, now you have a function and it will turn out to be also a least upper bound of your chain of functions in S. So if we have CPO, we know that if you have a codomain being a CPO, chain join exists for a CPO, and it has a list element. And if you use and if you do the pointwise extension to obtain an order over your function space, then your function space also is a CPO, and you can talk about doing a join of the chain of function. And this is basically why I can liberally say, I want to do the join of my G0, G1, G2, G3, and so on. And it will make sense. It is because this says it makes sense. The only question is, does it really answer the question about recursive program? So for that, I need to talk about a few more things, a few more definitions. And then I will be able to state the theorem that says what I do to function, what I do to using a sequence of approximations and take limits to declare that that will be the answer to my recursive program question. There will be a theorem that says, yes, this works. Suppose you have two partial orders D and E, and suppose you have a function from D to E, and this time both the domain and codomain are partial orders, and I'm very lazy, so I will be using the same partial order symbol for both partial orders, even though maybe I should not. But F preserves order, we say monotonic. This one you kind of also have seen from real analysis in some form. But here I want this form, and I just need this form. If X is less than or equal to Y, then when you can apply F to both sides, and you will still have the less than or equal to relation. So that would be monotonic. Now suppose that D and E are furthermore stronger requirement. They have to be CPOs now, because I will be talking about chain joins on both sides. And so suppose I have a function from D to E. So some kind of nice function. So monotonic is the nice kind of functions you expect if you know that your domain and codomain are partial orders, and suppose you don't know anything further. So that would be monotonic would be the nice kind of functions. So what about the nice kind of functions for CPOs, which furthermore has promises that every chain has a join, and you also have list elements. So we call it continuous, and there's a way to see why this is related to continuity, continuous function from real analysis. That would be a long story, but there's a way to relate them. But actually, you know what? Maybe if you imagine that chain join stands for some kind of limit, is something analogous to limit, then this version of continuous set, it preserves chain joins. If you're trying to do F of a chain join of S, then it is the same as computing the image of F on S and doing a chain join on the elements of that image. So F preserves chain joins or limits. And in that sense, you can start to see maybe it is analogous to continuity in real analysis, because you also expect a continuous function over there to preserve limits, to commute with the join operation. And there's a theorem, and it's a short proof, but I don't even have time. But I don't have time to go through it now. But if a function is continuous, then it is monotonic. And so this is a strictly continuity is a strictly a stronger requirement. Okay, so this is a theorem that I'm going to rely on, and then I will say, right. So suppose I have a CPO. So let's say the set is D, and the partial order I write, that is a symbol for my partial order. Suppose that is a CPO. So chain joins exist, I have a list element and so on and so forth, so that I can do that. So suppose I have a continuous function from D to itself, the capital F. So now I am interested in this kind of equation. Is there a solution to this kind of equation where you say, I want an element P in D so that it is equal to F of P. F of P gives me back the same P. Do we have some elements that satisfy this equation? And moreover, if there are many of them, since we also have a partial order, we can ask the natural question, which one of them is the smallest one? And the answer is yes. It exists. This equation has solutions, has at least one solution, and it also has a least solution. And of course, right, actually the uniqueness is also a little bit tricky, so I don't leave it as an exercise, but the proof on the next page has everything. So, and the solution, and that solution for the least solution, which is unique, will be the join of a sequence. So what sequence? So you construct your sequence from saying, hey, D is a CPO, so I have a bottom, so the first element of the sequence is the rock bottom. And then after that, the next element in the sequence is just F applied to the previous element. So it's bottom, F of bottom, FF bottom, FFF bottom, and so on. And the proof is on the next slide, but I just have 1 minute, but that's enough because I can now apply that to my scenario. So, so recall way at the beginning, I am exactly asking this kind of question, right? I write down an equation, G is defined in terms of itself. This is a fixed point equation. Does this have a solution? So to answer that, I have to construct this function capital F, which is a function transformer. If transform a function like this, right? So it's basically this part. So this is trying to say G of I plus 1 equals to capital F of G of I. And my capital F is trying to say the rest of that part without G of I, right? So I say so this function transformer, transform your function R. If you give it a function R in this space, then it will transform it to a slightly better function, a slightly improved function, still in the same space, but your function R, your new function will be, it will map an integer n to this kind of thing, but then at the right time, it will use your R. It will use your R to do the rest. And so my recursive program is really just trying to say G equals F of G. I want to define G in terms of F of G. Can I do that? Is this a valid definition? Is this well defined? What are solutions? Is there a solution to this equation? And is there a least solution to this equation? And the theorem says yes, such a G exists. There exists a G satisfying equation, and here's one of them. If you construct this sequence, which is what I did, but just in a more pointwise, pointful notation, and then you do a join, and I have explained to you how to do join for functions, but you have already seen it, also seen it intuitively. And the limit of this sequence, this limit will be a solution to this. So that justifies why I did what I can do what I did at the beginning. I construct a sequence, take a limit, and merge all those functions, and I would say that will be the mathematical model of my recursive code. So I think I can end now, and this is the book I like to read, and I learned so much. Yeah, a lot of things, and the proof of many of the proofs, of course, I also just borrowed from this book. So this is a cool book. I don't know whether we are at the second edition or third or fourth or whatever, but whichever edition you can find is good. Of course, the newer the better. So thank you, and I think I will be, yeah.
Okay. Yeah, thank you very much, Albert. I have never really dipped into theoretical computer science. I feel like I just learned a ton about partial orders. Before we get into question time, we're going to pause for a moment, and I'll ask you to fill out a survey so that we can give some feedback to our speakers. So we'll pause for 3 minutes, and then we'll have a question period. So thank you very much. That was awesome.